In section 5.2, I'm going to discuss Newton's first law and net force. Specifically, I'm going to define inertia and describe its properties with Newton's first law of motion. I'll introduce the concept of net force and describe how a net force can affect the motion of an object. And I'll demonstrate how to analyze free body diagrams in a few examples. Newton's first law of motion states that when the forces that are acting on an object are acting in balance, the object's motion, or its velocity, is going to remain constant. And this property of matter is called inertia. Inertia describes an object's resistance to changes in its motion, resistance to changes in its velocity. So if an object is at rest, it wants to remain at rest. If an object is moving, then it wants to continue moving with that same speed and move in a straight line. It wants to maintain a constant velocity. If there's an unbalanced force on an object, then that object's velocity will change. Another way to say that is that it's going to accelerate. So balanced forces result in an object maintaining its velocity. Balanced net forces will result in an object changing its motion. So force is a vector quantity, which means that force has a direction. And so when we add forces together on the same object, if forces act in the same direction, their magnitudes add. Forces acting in opposite directions will have their magnitudes subtract from each other. And so we can add forces up in a way so that they can balance out or cancel out in a particular direction. For example, a stalemated tug of war where the rope is not moving will have equal forces acting in opposite directions, and so equal and opposite forces balance or cancel each other out, resulting in the tug of war rope not moving. The total of all the forces acting on an object is what's referred to as the net force, and it's the net force that determines the effect on an object's motion. Remember that we must add forces up as vectors. We have to consider their directions and add them appropriately. We have to treat the x and the y directions as separate things. And if we have balanced forces, that means that the forces are all going to add up to zero. A zero net force results in zero acceleration, and the result of that is a constant velocity. What's constant velocity look like? Well, an object is going to move in a straight line at a constant unchanging speed. And we should note that that constant unchanging speed may be zero. So we may have zero velocity, we might have non-zero velocity, but zero velocity is also a special case of an object having an unchanging speed. If we have forces that are acting in an unbalanced way, then we'll have a non-zero net force. A non-zero net force implies a non-zero acceleration. And a non-zero acceleration means that the velocity will not be constant. It's going to be changing. And there's a few ways for velocity to change. The velocity can speed up, slow down, or we can change the direction. And the direction of it speeding up, slowing down, or changing direction is going to be in the direction of that net force. So it's the net force that determines how the velocity changes. So in the case of one-dimensional motion, we need to be able to describe whether an object is going to speed up, slow down, or move with a constant speed. If we have an unbalanced net force acting on an object, you need to know that the object will accelerate, and it will accelerate in the direction of that net force. Net force and acceleration are always in the same direction. So if the net force and acceleration are in the same direction that the object is moving, the object is going to speed up. So maybe we have an object moving forward. If a net force acts forward on an object, that object speeds up. If the net force and acceleration are in opposite directions to an object's velocity, then that object slows down. So maybe an object is moving forward and there's a backwards net force on it, and that object will slow down. In the case of an object experienced experiencing balanced forces, where there's a net force of 0, that object is going to maintain a constant velocity or remain at rest. Remaining at rest is a special case of having constant velocity. So how do we measure force? In the United States, we use units of pounds to measure force, but in science, we use an SI unit that's defined as the amount of force that's required to accelerate a 1 kilogram object at a rate of 1 meter per second squared. Multiplying those two numbers, we get our standard unit for force. It's the kilogram meter per second squared. And that's a real mouthful, so we give it a nickname named after Isaac Newton. So a Newton, represented by a capital letter N, is our standard unit of force. Now, if we have a standard, something to measure force from, and that 1 Newton is our standard, then we can measure force. There's two very basic ways that we can measure it. We can put an object on a balance and measure the force by comparing it to known amounts of weight. Weight, of course, is a force. Alternatively, we can use what's called a spring scale, because springs will stretch or compress a predictable amount based on the spring's properties and the force that the spring has to provide. On the next few slides, I'm going to do some examples where we have to analyze free body diagrams. In this one, we have a monkey that weighs 100 newtons sliding down a rope with a tension of 100 newtons. So part A, we have to draw a free body diagram. Whenever we're doing a force problem, you should always draw a free body diagram. This is like step 1 to every force problem that we're ever going to do. So here's the dot to represent our monkey. We have a weight that acts down, and we have a tension force that acts up. And we know the value of these two forces. We know the weight force is going to be 100 newtons. We know the tension force is going to be 120 newtons. So you don't have to write the values of the forces in a free body diagram, but I find that if we know the values, that it does help to include that. For part B, we want to determine the net force on the monkey. So to find the net force, we have to add the forces as vectors. So in this case, the upwards force of tension is going to get a positive sign because that's going to act upwards, and the force of weight that acts down is going to get a negative sign. So we're going to add a negative weight force to the tension force. And of course, this is just going to be the difference in magnitudes of these two forces. The difference, which is our net or total force, is 20 newtons. And notice this 20 newtons ends up with a positive sign. That means that our net force is directed upwards. Now, the net force, while it is upwards, we never draw net force into a free body diagram because net force is not a force. It's just the total of the forces. It's a useful idea that helps us predict the effects of motion on an object. For part C, we want to describe, is the monkey's speed of descent increasing, decreasing, or remaining constant? So in this case, we need to recall that the monkey is moving downwards. And so the velocity of the monkey is opposite the net force and the acceleration of the monkey. So when an object's acceleration and velocity are in opposite directions, that object is going to be slowing down. So the monkey is going to be slowing down as it slides down the rope. In this next example, we have a car that weighs 5,000 newtons that moves forward with an increasing speed due to an unbalanced net force of 500 newtons. We know there's a drag force of 300 newtons acting on the car, and part A wants us to draw a free body diagram for the forces acting on the car. So we'll have a weight force that acts down, and we know that that weight force has a value of 5,000 newtons. The car is in contact with the ground, and so the ground will exert a normal force that's perpendicular to the surface of contact, perpendicular to the ground. And because we know the car does not move up or down, we know the forces in the up and down vertical direction have to be balanced. So we know that this normal force has to be equal to the weight. So the normal force will also equal 5,000 newtons. There's going to be a drag force that acts backwards, and we are given this value that's 300 newtons. And there has to be some applied force that causes the car to move forward with an increasing speed. There has to be an unbalanced force in the forward direction. And we can figure out the magnitude of that applied force by taking the given value for the net force. So we know the net force on the car has a value of 500 newtons. And we also know that the net force is going to equal the applied force minus the drag force. The forward force minus the backwards force has to equal 500 newtons. Well, we know the value of the drag force is 300 newtons. And so the applied force acting on the car has to be 800 newtons. So there's 800 pushing forward, 300 pushing backwards, resulting in a net total force of 500. All right, in the next example, we have a skydiver that weighs 900 newtons falling with a constant speed. Part A wants us to draw a free body diagram. So here's the skydiver, and the skydiver is being acted on by a weight force, and we are given the value of that weight force as 900 newtons. There's going to be an upwards drag force, and we know that drag force acts upwards because the skydiver is falling downwards. Drag always acts opposite velocity. So now we have to determine the magnitude of all the forces acting on the skydiver. Because the skydiver is said to be moving with a constant speed, that implies that the net force acting on the skydiver is 0. So the drag force minus the weight force is going to have to be 0, which implies the forces are balanced. So the drag force has to be equal to the weight force. We know the value of the weight force is 900, so the drag force also has to be 900 newtons. In this example, we have a model rocket that weighs 30 newtons that moves upwards with an increasing speed due to a net force of 150 newtons. The rocket experiences a drag force of 20 newtons. We need to draw a free body diagram showing the forces acting on the rocket. So here's the rocket, and the rocket has a weight force that acts downwards, and we're given the value of that weight force as 30 newtons. Because the rocket is moving upwards, that drag force is going to be acting downwards. Drag force always acts opposite velocity. And again, we know the magnitude of that drag force is 20 newtons. In order for the rocket to move upwards with an increasing speed, the net force is going to have to be upwards, and that net force is 150 newtons. So there has to be an unbalanced net force upwards, so there has to be a force pushing upwards, and that, of course, is thrust. And we're going to need to find the value of that thrust force. So I need to write an equation for the net force to determine the magnitude of that thrust force. And I know the net force is going to be equal to 150 newtons. Now, the net force is also the sum of all the forces, adding up all the forces. So the thrust force is up, that gets a positive sign. The weight force is down, so that gets a negative sign. I'm going to subtract the weight. And the drag force also gets a negative sign because it is down. And these three forces all have to add up to 150. And that is going to be a positive 150 because the net force is upwards, gets a positive sign. So now I can just fill in the thrust force minus the weight force, which is 30 newtons, minus the drag force, which is 20 newtons, has to be 150 newtons. And when we add 30 and add 20 to either side, that gets us a grand total of 200 newtons acting upwards to provide a net total force of 150 newtons. This example, we have a man that weighs 800 newtons that steps on a scale that's in an elevator. And he notices that the scale reads only 700 newtons. Well, that's weird. How could he lose weight? Well, you're going to see that he actually didn't lose weight, and we can show that if we analyze the forces. So here's the man, and the man is being acted on by the force of gravity, aka weight, and we're given the value of that weight as 800 newtons. The man is stepping on the scale, and the scale is a surface, so that it will exert a surface force called a normal force upwards on the man. And the 700 newtons that the scale reads is the normal force. Bathroom scales will read the normal force that they provide on the objects on top of them. So we need to determine the net force on the man for part B. So the net force is the total of the forces. So we're going to add the normal force and the weight force, but we have to remember to add them as vectors. The normal force is upwards, so I'll give that a positive sign. The weight force is downwards, so I'll give that a negative sign. And so the net force is going to be 700 minus 800 for a total of negative 100. Now, that negative sign, that indicates that the net force is downwards. The magnitude of the net force, if you're ever asked for the magnitude of the net force, we ignore the negative sign, which just indicates direction, and the magnitude of the net force is 100 newtons. And so we know that net force is down, which means the acceleration of the man is down. The elevator is accelerating downwards. There are two ways for this to happen. The first way is for the object to be moving downwards and increasing its speed. You've probably experienced this when you step on an elevator, press the button to go downwards, it starts moving downwards and is speeding up, and you feel lighter than you normally do. That is what's happening to the man here. He feels like he weighs less, but he doesn't actually weigh less. The other way for this to happen is for the object, for the elevator and the man to be moving upwards and be slowing down. Again, you've probably experienced this when riding an elevator, where the elevator is moving up, but it needs to slow down to let you off at the floor that you want to get off at, and you feel just momentarily lighter than you normally do, which leads us to this idea: could the scale on the last slide, we saw that when the elevator accelerates downwards, the man feels lighter than he normally does. And so, could the scale ever read zero? Could he ever feel like he doesn't have any weight? Well, let's quickly discuss this. Well, the net force, which we know is the normal force minus the weight. And if we want the normal force to be zero, well, if we stick a zero in for normal force, we just get minus W, right? The net force is just negative W. Well, what would the free body diagram look like for this situation? Well, it would look like we had a weight force acting downwards. We only have the force of gravity acting on an object. Well, what's this? This is free fall. An object that is only being acted on by gravity, which is the weight force, is an object that's in free fall. Objects that are in free fall will feel as though they don't weigh anything. And so that leads us to the principle of apparent weight. How do you get your sense of having weight? Well, you get that from the supporting force. You don't get that from your weight. You get it from the force that's supporting you. Usually, this is a normal force. If you're standing on the ground, you get your sensation of having weight by the ground applying a force to the bottom of your feet, and the force that the ground usually applies to the bottom of your feet equals your weight. So normally, your apparent weight and your weight are the same thing. But you've seen that if you are accelerating up or down, then your apparent weight will be greater than your normal weight if you're accelerating up, or less than your normal weight if you're accelerating down. And so this is just the apparent weight is how you feel. It's not your actual weight. And for the special case where you feel like you don't have any weight, where there is no supporting force acting on you, we refer to this as weightlessness, and you typically will see this in astronauts because objects that are in free fall are weightless. Well, orbiting objects are in free fall. Astronauts experiencing orbit are weightless, and so we get these really neat videos watching astronauts in free fall in orbit. But I want to be careful in explaining this because we say that an object is weightless, but it's really kind of a misleading term. Objects cannot be without weight. If you're in the universe, there's other objects exerting a gravitational force on you. Therefore, you have weight. You can't ever have weight, but it can seem like you don't have any weight. And so, probably the better term for this is apparent weightlessness. But normally, we just refer to this as weightlessness.